Okay. And so yeah, tell me which question you'd like me to look at. If none of them, that's fine. We'll just move to the probability unit module.
Hi, good morning, Professor.
Oh,
I wanted to email you about a particular question, but I think that I got the answer as soon as I started reviewing it. But
okay.
it was the in my case, it was the one advising about the study with the dean and the
Uh,
if it was either experiment or if it was a double-blind experiment. In my case, I selected that it was an experiment, but not a double-blind experiment, but the correct answer was an observational study.
yeah.
Um, so I think I got the answer as soon as I reviewed it, but I really wanted to see if it could be discussed.
Okay. When you read these problems from the module on experimental design and surveys, you spend some time thinking about what makes an experiment, right? So to make a good experiment, you needed to have randomization, replication, and representation or control, right? Randomization, replication, and control. The problem here is there's no randomization. And they're kind of inseparable because without randomization, it's really hard to attribute like the cause. So here there's no randomization. You kind of think it's there because when you're reading it, it's obvious they should do that, but it doesn't say that. That's the problem with this, right? So a dean would like to determine if students perform as well in online distance education sections of a course as they do in a regular in-class section. So what they should do to do a gold standard study is to create an experiment and randomize students into the sections. So students sign up to take this course, but then they split them. And so they label all the students that sign up and they start to split them. You're going in the online, you're going in the in-person. So the way they do that is they label all the students and then they start to randomize with a random number generator. There's none of that here. So what's the problem if students are not randomized? Well, the students who like online classes, who are good in online classes, take the online class. And students who don't like online classes and they like the interaction in class with students and with professor, they take the in-person class. And so that is a problem of self-selection. And you need to control against that because there is a bias there that the students will do better because they ended up in the online class and they already know that they're good at online classes. So you're not really testing, um, you're not really testing the method or the modality. All you're doing is looking at whether students are appropriately self-selected themselves. You're not. So self-selection is really important to control against because it's confounding the result. Does that make sense? Better sense? More sense?
Yeah, no, it does.
So
Then
the key
at
word
the
is randomized, and you assume they did it, but you can't. It's not there. It's in that paragraph.
Yeah, it does make sense. Thank you so much.
Okay, sure.
Told you, tricky questions.
They are. And
I got that one wrong as well, and I thought as like you did. So yeah.
maybe in the future I can leave this up as a mock because most of the tests I have a question like that to clarify or to stress the importance of randomization. Okay. What else? Let's go back.
Can you discuss question number 9, please?
Okay. Number 9. Now, is this the same 9 that you had? Because they were randomized exams. So is number 9 about drugs?
water, bottled water,
Okay, we got to
bottles. Let
find
me
a bottled
see.
water. Because they were different order. Is there a name on the, oh no, maybe no, you don't have the names. Yeah, I'll find it. I think it was a normal distribution problem, right?
Number 15.
Yeah, it was from the normal distribution. Contents of bottles of water follow a normal distribution with a standard deviation of 4. What proportion of bottles have fill volumes within? Okay, so this kind of a statement is studied in the homework assignments. And the homework assignments are filled with old exam questions. Sorry, filled with old exam questions. And so you would understand better if you were able to get through that or saw that. Within is more like, is like a between statement. Let's just do that. I'll show you that. There's a lot, it looks like there's a lot of information missing, right? Yeah, I'm just going to copy it. Oh, there's some questions in the chat too. I'll get to. So this is the information that they give you. They don't tell you the mean. They just tell you the standard deviation. But let's proceed even in with the absence of information, because the way they ask the question helps you out. They said, what's the chance that, or what proportion of bottles will have fill volumes within 1 milliliters of the mean? So the mean -1, the mean +1. That's what you're looking for. So that is the step you need. There is a problem like that in the homework, but maybe you might have skipped it or figured it out a different way, or you didn't realize how to get that answer. So this is within. And because of that, what happens next is the next step is to standardize. When I standardize, it doesn't matter that I know what the mean is, because I just subtract the mean and divide by 4 and turn it to a z. And they cancel. So you don't have to know the mean. Look at the power of the mean. Hey, I don't have to know the value of the mean to want to understand behavior around it. So when I do this, I end up mu minus mu. Doesn't matter what they are, they cancel. And I'm actually calculating the proportion that C is between 1/4 . So it's standardizing it. So now we're on the standard normal, and we're within a 1/4 of it. 0.25. And then we go to the table. Doing a bad job with my lines. So, oh, sorry, it's a 0 here, right? So what should I do? I want this area here. The tables only give me the left side. So I look up 0.25 negative on the table. What do I get? I'm going to table quickly here. So I'm looking for negative 0.25. And that's 0, 1, 2, 3, 4, 5. It's this one here. Is that correct? So it's almost 50%. It's 40%, 40, 1, 3. And then on the positive side, to do the between, I mean, there's a couple ways you can do this because it's symmetric. So that's for the negative, and for the positive, 0.25. Well, that's at the top. So over here, 0.5987. And then you subtract them. You do big minus small. You get the difference. Or you can just take 1 minus 0.04, sorry, 1 minus 0.4013, but 2 of these. Because you want the in between. That's another way to do it. Should give you the same answer. Any questions so far? Did I write anything wrong? Did I transcribe? 5 minutes.
Got it. Thank you.
Okay. Let me confirm my numbers. So yeah, that was not a little trick, a little twist. But in general, you guys did quite well. I guess you're feeling like you didn't because you had to put a lot of work into it. It wasn't immediate, which is good. That's why I give you time so you can learn it through the process. I'm glad you took up the challenge. Okay, so and that's an option, I hope. It's, I'm gonna double check. Yeah, it was one of the alternatives with 100%. Okay. No questions about that one anymore? So I'll go back to the test. See here, you see how it works in the I can give partial marks through the system, which I like. And I have to indicate which one is 100. You see, I can give partial marks. That's in the case if a lot of students have made the same error and different interpretation of the problem, so then I can award them something or all the points as well. Okay, any other ones? Everybody knows how to see their grade, right? In the platform, and you can see which questions you got wrong, I presume. So,
Profesora, en esa pregunta yo puse 68.6826, o sea, como que el porciento, porque pues como estaba, o sea, la cantidad que estaba buscando cae bajo la primera desviación estándar, pues yo entendía que pues era como que tú sabes, como que en qué proporción de la distribución normal, pues caía esa cantidad que estábamos buscando, porque como no nos estaba dando la media, pues por eso fue que puse esa. No sé si alguien más pues interpretó lo mismo que yo interpreté o...
Yeah, anybody else feel like they did the same?
Sí, yo también hice más o menos el mismo racionamiento, por eso fue que pregunté, pero fue que hice el mismo ejercicio. Lo único que me fallé cuando en la parte esta de la estandarización de el min menos el 1 menos la min, ahí fue que entonces me equivoqué. Pero sí, hice más o menos el mismo racionamiento de la compañera. Y
Pero
cuando me dio 68, entendía que estaba dentro de la contestación correcta.
ajá, y estaba, ya. Pero entienden la respuesta correcta. ¿Ustedes sí entienden ahora?
Sí, sí.
Sí,
Okay.
sí.
Pero...
I can give you guys half points for that. You did half if you guys want. I can give you half points, but then everyone gets half points. Let's see. I'm going to go back to. So what you have to do when I give half points, I have to regenerate. Do I have to regenerate? Yeah, I have to regenerate the grades. Then you can see it. So let's see. I'm going to go. So this one here, 50%. Okay, so just wait until I'm finished and then I will regenerate the grades and you can see the extra points.
Gracias.
Thank you. Any other questions people have? If there's no questions, what I'm going to do, we're going to go to review probability. So you had 2 weeks to work on probability. Maybe you didn't work on it the first week because you were recovering from the exam. So then I gave you an extra week. Probability was module 6 and 7. So 7 didn't have any extra notes. It was just to take more time with the module 6 and the other half because it was kind of split in half. So I want to do an overview of what you learned there. Maybe you haven't finished yet, but maybe I can highlight some of the topics and offer some assistance. For next week, you're going to begin module 8. And I think probability is the most challenging, I think, but I don't spend a lot of time on the final with it, but you do need to know probability and some basics. Like that's I I think you guys can make it with probability, but it's going to feel different than the other kinds of questions. It's a lot in probability, and mostly because you may have never encountered probability before. So, but I try and depend a lot on your intuition. Okay, are there any other questions for me about the test? No? So let's look at, let's get out of here.
Professor, I was looking at module 7 and I see that there's assignments in Spanish,
Uh-huh.
but there's no English version. Is that
Oh, you need the English? Do you need the English?
it would be good. I think it would be good.
Let's see. Yeah, because this course was, I was told I had to make it in Spanish. So I wasn't making it bilingual, but I made it like the best I could in Spanish tools. But yeah, let's see. Sorry, in 7.
Sorry, it's that I've been studying everything in English, and so it's kind of strange to go back to Spanish. So I'm kind of used to something. Yeah, I hope you understand.
Yeah, so these two here.
Yes.
Yeah, and again, it's probability. So you really need you really need to understand what's going on. Maybe I can have my TA do it. And the solutions are written. Oh no, I have them. Oh wow, look what all this work I did.
Thank you.
I must have, trying to think if I have them. Oh, this one is in English. I'll look for my English version because I probably had them in English and had them converted. And then this one too. Right. I'll see what I can do. But worst case scenario, you just copy and paste into Google. But I know it's awkward going back and forth. Okay, so let me make a note about that. Okay. Right. So I begin with a discussion in the notes about what is probability. We use the idea of proportion or percentage, and then I introduce the idea that if you have a view of all the possible outcomes, we can talk about, like when we talked about the normal distribution, and I that's where I started to talk about what is a probability. So if I believe I have a relative frequency histogram and I assume I'm looking at a distribution of all possible outcomes, I can start talking about the chance of something occurring, and then I interpreted that as probability. So the P that we use in solving problems can represent frequency, proportion, percentage, and probability. But then I go a little further here and really try and reconcile some of the poor interpretations of probability or what it is, or expectations, and this idea of independence. And I mentioned, okay, so the example, if you heard it, the example that I mentioned is, okay, say that you have a young person in your life, a child or a nephew or a niece, and they are curious and they're playful, and they spend some time challenging this notion. Though they take a coin and they flip the coin, and the coin can turn up a head or a tail. And imagine that they flip the coin 10 times and they get a head every time. And they tell you, I got a head every time. Does that change the expectation? Or does that change? Okay, first of all, ruling out anything's wrong with the coin, does that change my chance of getting a head on the next time, because I had a head every time before that? And what do you tell them? How is it that I'm told that it should be 50% chance that I get a head and 50% chance that I flip for a flip and I get a tail, but all 10 times I flipped, I got a head. So should I expect a head on the next try? And what is your answer to them when they bring this to you or raise this question, or they're challenging the convention? What you should say to them is, you just have to keep on flipping. You haven't had a chance to see the long run relative frequency. I don't know if you're going to say it like that, but you haven't had a chance to see the behavior of the coin yet. You need to see many observations before you see the tendency of a coin. So here's just an example. So this can be done now, with computers. We can look at this behavior. If you toss a coin and you run this experiment, the first one that you toss, they recorded it here, and it's like comes up ahead, so they mark it 100% heads. But then they flip like 10 times, and 5 of them were heads and 5 of them were tails, so they mark it here. And then they notice that, okay, so they got 50%, but if they flip 12 times, they get a few more, they get 6 heads rather than 5. So it's unstable. It's an unstable phenomenon until you flip it enough times. And then you're pretty sure if you flip it enough times, you're going to see this 50%. So if they flip 500 times, 250 will be head and 250 will be tail. So that's what probability is. It's a long run relative frequency. And that's really important. And I use that a lot. And then I've introduced the idea of independence. So what is independence? What is independence? Someone tell me in their own words, or what they understood, or help me explain to the rest of the class, because this is a really important concept. Okay, back to the coins. Here's the coin example. You can put it in the chat, or you can say it out loud.
Well, it's already in there. The fact that the fact that one event does not affect the other event, no matter how many times it happens. So
just to be specific, the point is that the fact that it was head on 10 trials, it doesn't affect the probability of a head on the subsequent trial. So the chance of a head is still 50%, even no matter what happened in the past. It doesn't change the probability distribution, or the fact that it's going to be 50% chance of a head, 50% chance of a tail. Okay, so it doesn't affect the probability of outcomes, or the distribution of outcomes. Okay, good. So then I went through a few different, I expanded the idea of flipping coins and introduced this concept of a probability distribution. We created this together. So I defined just first how we can create, so there's questions like this in some of the review exercises, like where I just ask you to create the sample space. And so you have to think about how to lay this out. And I went through this with a student the other day. Think about when you're thinking about seeing repeated events, think about them as, outcomes. Let me show. So you can get into the habit. So for the 4 coins, there's 4 possible outcomes, or 4 slots, or the outcome is really the outcome looks like this every time, but we begin with the issue of how many outcomes are there. Okay, so the way to think about this is all of them are going to look like this, but they're going to be head or tail on each. So there's 2 possible outcomes on the first coin. So you can think about flipping the coins side by side by side, right? So they're all laid out on the table. You can do them all at the same time, or you can do one at a time. And you see that either it's a head or it's a tail on the first one. So there's 2 possible outcomes. On the second try, what are the outcomes? There's 2 possible outcomes, and on the third and on the fourth. So in this way, this is where this idea of all possible combinations of these outcomes on each individual try create 2 to the 4 or 16 possible outcomes. And then you can spend time listing them, right? So you make a list. So I go from the idea that, okay, there's 16 possible and you can write them all. You begin with head, head, head. And then you say, okay, now I'm going to make, put a tail in there. So you make a list, and in the process, you end up with, you guys are seeing this, right? So in the process, you're going to end up with these, and I've ordered, well, in here, I just put them out, but then I change the definition of the random variable, and I call the random variable the number of tails and 4 flips. So now I can group together the similar looking outcomes and talk about the possible outcomes themselves: 0 tails, 1 tail, 2 tail, 3 tails, and 4 tails. Now this is a different variable, the number of tails and 4 flips. And in module 8, you will learn that the pattern of this is known as a binomial. And you're going to look at different problems that are binomial problems and solve them using the pattern. But for now, I just use it as an example, and I talk about this probability distribution where each of these, because there's 16 possible outcomes and they're equally likely, I create a distribution where I say the chance, so I'm in by grouping them, the chance of seeing 0 tails is 1 out of 16, but the chance of seeing 1 tail is 4 out of 16, 2 tails is 6 out of 16, and so on. I'm just counting them. And I create this distribution that's supposed to look like, it doesn't look that great like one, but it is supposed to be like a normal distribution. Now, I mentioned this in module 8. I bring it back and I bring it to module 8 where I talk about, over here. So here it is, here. So you have here the table, and you have the distribution drawn, graphic. Now, what's the difference? So it's really important when I teach to try and relate what you learned before so it doesn't seem all so new, right? So you're just variations of what you've seen before. So how is this the same or different from something like the normal distribution? What looks similar? What's different? Put in the chat. Okay, let me see the chat. Okay, so Juliet says it's symmetric. Good. It's symmetric. Okay, so that looks that's a similar feature. Is this a normal distribution?
Yeah.
Who thinks it's a normal distribution? Jennifer? Put it in the chat. You think it's normal? Okay, so what you guys are seeing is it looks okay. Alejandro has a point there. Read Alejandro's point. Okay, and Ashley's saying, okay, like it looks like kind of like, so what it is not normal, okay, but it looks symmetric. So be careful. It's symmetric. It's not normal. Normal requires that you have first of all, that it's continuous. This is not continuous. What do we call this kind of distribution? What do we call this kind of variable? Sorry, this variable. So it's not continuous. What kind of variable is it? What are the possible outcomes? Look at them. How many outcomes are there?
Discrete.
Excellent. So it's discrete, right? Because how many outcomes are there? 1, 2, 3, 4, and 5. That's it. Not infinite. There's only 5 possible outcomes. So it's not continuous, it's discrete. So that's first why it's not normal, because normal is a continuous distribution. What you are seeing though, that it is symmetric, you're right. And it's, it's kind of spread out, but it's not normal. And I'm going to, you're going to see that there is a relationship, however. So you're sensing there is a relationship that looks bell-shaped, it looks symmetric. So there is a relationship in very specific cases between a binomial distribution and a normal distribution. And you're going to learn about that in module 8. Yeah. Okay. So hang in there. You'll see this again. But for now, it's discrete. It's not continuous. Now look at this. If I go back, okay, so I'm going to go back to what we were just talking about in the beginning. So this is the same exercise we were just talking about here. Look at it here. X equals 0. So the outcome, no tails, is 1 out of 16. Just because the drawing here, this is 1 out of 16 because there's 16 possible outcomes. This is 1 out of 16. If you are looking at a normal distribution, what would be the chance of X equals 3 of a normal distribution? X equals 4 of a normal distribution. What did we learn about normal distributions? Or continuous distributions? If I ask you the probability X equals 2, and I tell you that X is a normal distribution with mean something and standard, this is going to be 0, okay? For continuous distributions, equals will always be 0. Do you remember that? Some of you remember, some of you don't remember. So for a continuous distribution or for the normal distribution, whenever I ask you, what is the chance that X equals 38 or X equals something, it's always 0. And I explain that because it's infinite, to be at just one value, the chance is 0. There's no density at one value because of the infinite nature of the outcomes, right? Instead, we talk about a range of values. And so you always have X either to the right, to the left, or between two values. But in a discrete distribution, it can be equal. Okay, it can be equal. And so for instance, I create this distribution, and then I can ask you questions that look like I'm asking you questions about the normal distribution, but I'm not. I'm asking you about this distribution. So we can say, what's the chance or probability that X is greater than or equal to 2? So what do I do with this? How do I solve that with this new table of values or this new distribution? What would you say the answer of that is?
La escuela que lo enseñó a meterse todo el trululú en la boca. ¿Cómo se sabora el trululú? Mira, eso sí es feliz con un trululú. Coge el otro pedacito. Coge, coge, ven. Coge. Coge.
Okay, make sure you're muted. All right, so where were we here? Oh, I lost my images. All right, so what do we do? Yeah, you're writing in the chat. So you're going to get the answer, you have to collect everything greater than or equal to 2 and sum them. All right, you sum those. And you get, yeah, 6 out of 16, 4 out of 16, 1 out of 16. Thank you, Damaris. Exactly. And Juliet has it right. 11 out of 16. Okay, so you sum. And so it's a different procedure, but the same idea that the symbol greater, less, and now we have to be careful with the equals because the equals matters now. Okay, so that's another difference, is that the equal, the bar matters. With the continuous distribution, it didn't matter because at equal, it was always 0. It didn't add any probability, didn't add any density, didn't add anything. Okay, so it does matter here because it's a value here at 2, and I add them each up. Okay, so those are the differences, but some things look similar. Whenever you see a question like this, search for what is X, what is the distribution. So now you have learned about the normal distribution, but I spent module 6 and 7 talking about all sorts of distributions. I group them. Okay, I group them into a few of them so you're not overwhelmed. In fact, there are, I don't know, hundreds of distributions that have been derived by statisticians, and from those basic forms of distribution, they have infinite possibilities. Like the normal distribution can be infinite different kinds of normal distributions, but we talk about the standard normal, and we use the standard normal to help us with predictions, right? So what I do then is, okay, so there's a lot of stuff in here about theory of probability that I spend time with that, but you guys work through that. What I really want to talk about right now is those different kinds of distributions, because that's module 8. That's what I spend time with module 8. Seven, sorry. So what I talk about are the different types of distributions here, and we begin with discrete distributions and separate those from the continuous distribution. So one example is the one we just discussed. Another one could be this one. Okay, so here's an example of a discrete distribution. If I can list the possible outcomes and they're finite, that is a discrete distribution. And these are the possible outcomes. And then I can graph it. Now, this one is not symmetric, right? This one is not symmetric. It's not binomial. It was derived from several observations or observing the life expectancy of a robot arm over time in a manufacturing process or in a innovation process. And it was determined that there's only a 5% chance that it breaks down in the first month. And then that the chance that it breaks down in the second month is 0.25. But what is the chance that it breaks down within 2 months? Or in 2 months or less? You would add these together, you see. What's the chance that it breaks down in 4 months or less? How long will this robot arm survive? What does it say? How do you interpret that?
Professor, could you repeat the question?
Yes, yes.
This, looking at this distribution, what is the life expectancy of a robot arm, of this robot arm? Okay, what's the chance that it will break down in 4 months or less?
One, right?
1 or 100%. Very good, very good, very good. So that's what it means. Exactly. Very good. So yes, this robot arm's not going to last very long. So they got to go back to the drawing board and work on it. But it says that the chance it breaks down in the first month is 5%. In 2 months or less, it's going to be 30%. In 3 months or less, it's going to be 80%. And it's 100% chance it's going to break down by the end of 4 months. Right? Very good. Okay, so and the worst, really things start happening in 3 months, right? This is 50%. This is a huge one here. And that's the spike that you see here. Now there's no density between these points, right? There's no values here of possible outcomes. It's either 1, 2, 3, or 4. So I can give you something like a general discrete distribution, and you have to interpret. Each time I use the symbol X, but I define it in different ways. So don't think it's always normal. Different kinds of distributions appear. The second type of discrete, let me see. Do you have any questions about it? The second type of discrete distribution is a very specific one called the binomial distribution. And the binomial distribution, an example of the binomial distribution is the one that we just looked at. Number of tails in 4 flips of a coin is actually binomial. So what makes it binomial? Is it the symmetry? No. Okay. Is it the are there specific features that make it binomial? Yes. All right. So we're going to talk about those. You are dealing with a binomial distribution as opposed to, I mentioned some others here, but I really test you on the binomial, okay? But there's other distributions that I mentioned, the Poisson distributions, the hypergeometric distribution, as different than the binomial. You're going to see in module 8, I'm going to try and help you distinguish between what's a binomial and what's not a binomial. But what you're going to look for are these things, okay? First of all, you should be able to complete this sentence when you talk about the distribution or you talk about the variable. If you can write that the outcome is going to be the number of successes out of n independent tries, then you probably have a binomial. Okay, so for instance, when we're counting the number of tails, there you go. Number of tails. Tails is known as the success. It's what we're looking for when we flip the coin. And we say out of 4, we only flip 4. We don't flip infinite coins. We flip exactly 4. So we need that, okay, for the definition or for the identification of it as a binomial random variable. And those tries need to be independent. What does independent mean again? Let's see if you guys can try and explain. What does independent mean again? In this context. So what we're going to be doing is observing. We're going to repeat a process that we're going to call an independent try. So we're going to repeatedly do something and look for something called a success. And we're going to count how many of those give us what we're looking for. Okay. And what we're looking for is called a success. The tries are called the independent tries, and there's n of them. So what do I need from this? So you can use as an example always in your mind is the 4 flips of the coin as a classic example. And again, you can flip them at the same time or one after another. You can flip the same coin, but the idea is you're repeating something that is identical. The probability of seeing a tail each time doesn't change for each observation or each trial or each flip. All right, so the conditions are there are only 2 possible outcomes each time you look to observe what you're looking for. The success is what we're looking for, and if it's not what we're looking for, we're going to call that a failure. We also have to know P, the probability of observing the success. And we need to know that we are flipping a certain amount of times, and that certain amount of times is known, and it's finite. You just don't flip and flip and flip. You have to know how many times you're going to try and observe the successes, okay? And that will create a binomial. And I give you some examples here to look at, but those are the 3 necessary criteria for a binomial scenario. I give you an example here. I will not do it. So what's the goal? The goal is to create or identify what's known as the parameters of this distribution. What were the parameters of a normal distribution that we needed in order to be able to solve or make predictions about outcomes? What were the parameters of the normal distribution that we always needed? Mean was 1, right? Yes, Eliximar, right. Damaris, mean and standard deviation. Very good. Those are the parameters. Those the population mean and the population standard deviation, just to be clear. You needed to know those, right? Otherwise, you couldn't go anywhere with the problem. Unless I was asking you to find the standard deviation, I gave you some different information to get it. But yeah, you need the mean and standard deviation to understand what to expect out of a phenomenon that's described as normal. In this case, what you need to know for the binomial are P, the probability of observing the success, and N, the number of trials. Is this helpful, or am I just repeating myself? Let me know if it's helpful in the chat, because I could just scoot ahead and we can do problems. You want me to just go ahead and do problems? Tell me in the chat. You can tell me privately in the chat. Okay. Okay. Okay, yeah, let me know. Okay. If you want me to just move on, just put it in a private chat if you feel like you're deferring from the rest or you're okay. Or deferring from the rest. Okay. All right. So the parameters. So yeah, this is just an overview of what you might have seen, right? Because you get hyper-focused when you're studying. Okay. So the binomial has 2 parameters, like the normal has 2 parameters. Other distributions have more than 2, possibly the parameters, or just 1. But in this case, binomial has 2, and it's N and P. And once you know N and P, you can make predictions. So first we have to identify what N and P are. So here's an example. Find the probability of seeing more than 5 people holding an umbrella on a rainy day if 100 different people are randomly selected and observed having an umbrella or not. The probability of holding an umbrella on a rainy day is known to be 10%. Okay, so in that statement, even though I've given you one of them, identify N and P. What is N? What is P? Yeah. Okay. So N is 100. What is P? Right. So the other number, right? So I just gave you 2 numbers. So now if you have too many numbers, you have to sift through and identify. But I just gave you 2 numbers, and one is 100, so that's the N, and the probability is P, the decimal value. But if I had other numbers there, you have to be able to identify what is the number of repeated independent trials and what is the probability each time of seeing a certain outcome. And then once you identify that it is a binomial because it satisfies the 3 criteria, we're looking for an umbrella. That's called a success. If there's no umbrella observed, we call that a failure. We know the probability of success because someone took the time, or some agency took the time to determine what's the probability of seeing an umbrella. Why do we care about this? Maybe we're deciding from where we operate a mall, and we want to know, we want to be sure that there's safety in entering the mall, like Plaza. And we have to have certain things in place if it's rainy at the entrance to catch the rain. So maybe they put out a mat to collect the water and create, a surface that people will not slip on. Or maybe they have some bags at the front entrance that people can put their umbrella inside and not put water everywhere, right? So they want to know how many people have an umbrella coming into Plaza when it rains, so they can put enough bags out that they're useful and they can have enough supply in case, on a rainy day, they can put out those umbrella bags. Okay, so there's a practical purpose for this. And so this is observed over a while to limit the number of falls at the entrance of the mall. I actually fell at the mall. I had this example in my notes for years, but I actually fell at the Galeria San Patricio. It was so embarrassing. So many people came out, but I fell there was no mat, no surface. The surface was slippery and I fell. So anyway, so we can predict with this information of P, the probability of success, and the number of trials. This is how we would write out that it's a binomial distribution. And then we can check or we can make estimates of what's the chance that more than 5 people appear with an umbrella. So we have to have, what's the chance that we have to have more than 5 bags at the entrance for people to put their umbrellas away. Okay, so you can actually generate the binomial distribution in Excel. However, I mean, you guys can use Excel, but for this problem, but I do expect to see you applying the formulas I teach you in module 8. But let me show you. I want to take a moment and show you how we can generate this distribution in Excel very easily. And I have the notation for this, and I put it on the platform, and I'll show you that as well. Let me get out of here. So here at this is at the top of the platform. I indicate how you can generate in Excel the standard normal distribution and the inverse for the standard normal. And then I taught you how to do this for just the whole distribution itself without the S. So just in general. And we're going to talk about the t-table later, but this is the binomial. So for the binomial distribution, you see, you can use in Excel binom.dist, and you have to mention these parameters here. Well, you have to mention K, and you'll learn about that, and N and P, and that you want cumulative. Cumulative means you want everything to the left, just like in the Z distribution, you want all the values up to, in this case, K. K is like X for the normal. Okay, so this is the notation for the binomial tables. If you say cumulative false, it will give you the value at it'll give you like the distribution that we saw at the beginning of the lecture today, where I just tell you exactly equals. It's, you know, the chance that X equals 0, X equals 1 equals. So if you say cumulative false, it will do that. If you ask for the left side, you have to say cumulative true. Then there's these other two distributions that are also in Excel, and there are others. And now I'm not going to focus on these for the test or anything, but I put them there to make you aware that there's other distributions. Okay. I'm going to go to Excel now. So here we are. Are we here? No, I have to share. And I'm going to write equals . And then not normal, but I'm going to write binomial. And I'm going to pick this one. And it asks me for the number. So binomial distribution always starts with 0. So we're going to ask for 0, and then we're going to ask for more. And then we're going to put the number of trials. We had 100, right? And the probability was 0.1. And let's say we just want false. We're going to say, or 0. We don't want it to be cumulative, so I can show you what it's like. Oh, what did I do wrong? I didn't put a comma. I had to put a dot. All right, so this is a very small number. I'm going to, let me show you. If I do it like this, so I'm going to put the values of the binomial. It always starts with 0. 0, 1, 2, 3. And I'm going to change this from 0. I'm going to use the reference of this cell here. And that's a very small number. But then you see that Excel is nice because it gives you all these decimal places. Otherwise, it would just say 0, right? This is a very small number. This is 2.6, but you have to have 5 zeros before it, or you have to go back. So it's going to have 4 zeros before it. It's going to be 0.22. Sorry, 0.0000265. But they don't write it because it has an exponential, and I can change that, I guess, the format. Let's see. Format cell. Just want it to be a number. General, I don't like that. There you go. Okay. Okay, so I can generate the entire distribution if I go to 100. So I'm going to do this. So maybe you don't understand what I'm doing right now, but you'll see it's helpful later. So these tables, like what I'm creating now is just a table. And you can actually find online, like before calculators were ubiquitous, everyone had a calculator or a computer. Tables were sold to make these calculations, and scientists use these tables. Binomial distribution is at the heart of sampling and experimentation. So, in fact, it was important to have these tables. All right, let's see. So there it is. That is the binomial distribution. And you see, and I can make it just for 2 decimals. Let's see if I make it for 4 decimals. Usually I like 4 decimals. Okay, keep that in mind. I'm just gonna put 4. There you go. So it looks less scary. And usually the tables just have 4 too. But that's the idea. So that one just became a 0 because there were so many zeros in front of it. So if there's 4 zeros in front, just call that 0. And that is the entire distribution. And you see, after 24, they're all zeros. There's so small chance. Okay. So what was this? This was the probability of having an umbrella on a rainy day was 10%. The chance that one person has an umbrella is very small. It's more like it goes up, right? It goes up. The highest it will be is 11 people have an umbrella on a rainy day with 12% chance. And then it just goes down. Now, somehow, what should all of these, if I add these together, what should they make? Oops. What should be the sum of all these? Should be 100, right? It should be 100. And yeah. Let's see. Yeah, 1 or 100. Let's see if it works. So if I sum these, it's 1. It doesn't look like it's going to be 1, but because they're such small numbers, but there's 100 of them and they all add up to 100% or 1. Okay, so that's just for you as a tool. What you're going to learn in module 8, like I promised, is you're going to learn the formula to actually calculate each of these, but then to answer questions. So the question that I asked in the notes was, what's the probability that X is greater than 5? So what do you need to do? So this is 5, but I want it to be greater than 5. So what should I do to calculate that? Let me put the formula here so you can see it as well. So the question was, how do I find out the probability that X is greater than 5? Just tell me the approach. What should I do?
Sería restar 1 menos la probabilidad de
Very good. Is that Jennifer?
sí.
Very good. Right. So if you want to know greater, so either you add all these up. I said greater than 5. So you have to add up at 6. You have to be careful now with the binomial. The equal means something. Okay. You can't ignore it. So if it's X greater than 5, it means go from 6 and up and add them all up. Or faster, she said, why don't we take 1 minus probability X less than or equal to 5. Okay, so you would add these. I'm going to sum these. and then 1 minus. Okay, so this is and I did it. Okay, so you don't have to like copy the numbers per se, you know, you do the dragging and that will do it for you. But anyway. Okay, very good. So this is the idea. I mean, if you didn't understand anything that I just said, it's okay. But this is the idea of how you can generate the binomial, how we use the binomial. We create a table just like the standard normal table is created for us with a certain values. In this case, we can create the entire distribution very easily because n is finite, right? Because they tell us exactly how many to repeat. Okay, so let's continue our discussion. So that's a binomial distribution in an overview. You can take a screenshot. You can try it yourself later if you need it. But still, you need to learn how does it calculate this? And how does it know what's programmed in there? And we'll talk about, you'll read about that in module 8 this week. And hopefully you're curious at this point to learn that. Okay. All right. So, that's the goal. So if with everything we've done so far, our goal is to make estimates, right? Alleviate uncertainty, know what to expect. So that's what we're doing. We're building distributions to do that. All right, so to recap, discrete distributions, there's the ones that I give you that you interpret. Discrete distributions include general discrete distributions, which I just give it to you, and then the binomial, which has a particular pattern, and I teach you how to analyze that. I teach you about the formula for deriving the outcomes, the chance of seeing certain outcomes, certain successes. And then there's these other two, I say unit 5, but then there's these other two distributions that are discussed in Newbold textbook. But I'm not going to go into this too much. Don't worry about this stuff. But they're just good to contrast with a binomial because they also use n, and they also talk about selecting, but binomial is very specific. So I just teach it in the context that as compared to the binomial, because I want you to understand how to see the binomial and not get tricked into thinking it's one of these. And you'll have that opportunity this week. All right. Here's another example. You should try it. All the answers are available in the notes. Okay, the other group of distributions are the continuous distributions. And the one that you know is the standard normal and the normal distributions. But there's a couple of others that you're going to learn, we're going to focus on in this class. One is the uniform distribution. And the uniform distribution also has parameters that we use to solve and make estimates, right? Compute estimate of what to expect. It looks like this, U and then L and U. L stands for lower bound and U stands for upper bound. And what it creates is a shape that looks like a rectangle. Not a curvy one, not a spike one. We're back to talking about continuous distribution. So this is like normal in that sense, but we don't need a table to derive probabilities because we know our grade school mathematics. We know how to do this. Okay, so the shape is going to help us. Here's an example. Okay, so the example is that you're told that the number of hours that students study is uniformly distributed. It means that the chance that a student studies a range of 4 hours is the same anywhere along the line. So if a person studies just a little bit, so their chance of studying 0 to 4 hours is this one, but their chance of studying another range would be 12 to 16. That's going to have the same probability. That creates what we say is uniform. Okay, so again, because we're in a continuous distribution, we only talk about ranges. We don't talk about probability at a point. There's no probability x equals. We can't do that. Everything is in ranges of values. Okay, so a best way to do this is the example that I give here. Let's do this example together and you can go back after. We'll do that in a second. I just want to mention the other continuous distribution that we learned was normal. And in module 9, you're going to learn about t-distribution that's related to the normal. Okay, so these are the distributions for the course, and that's it. Okay, I'm not going to teach you hundreds of distributions, but I encourage you, if you're interested in statistics, take another statistics course and you'll learn about different distributions. Okay, so let's try this problem, okay? What you're going to do is identify the lower and upper bound and make a rectangle, and then answer the questions. So let's spend 5 minutes on this. Okay. Let's leave it to you. One way to remember about the uniform is that any position along the number line is equally likely. But again, we don't like to say that you have a probability in a continuous distribution at a point, but that's what it looks like. At any point along the range of values, it has the equal height. So it's kind of like to be anywhere on that anywhere among the possibilities is equally likely. Uniform. There's no peak, there's nothing like that. So you're drawing a rectangle between -3 and 10. And I'm going to share my iPad. Not a very straight one. You can use a ruler or a straight edge to draw this. So this is the distribution. X is uniform between -3 and 10. And the question is, again, we're going to use X. The question is probability X greater than 5. And what's the chance that X is negative, less than 0? So we're going to do these two questions. We're going to solve these two problems. Using the rectangle. You don't have to use a normal. It's not a normal distribution. It's uniform. Okay, everyone has a drawing. Now we're going to partition the drawing. We're going to do the first part. And so 5 is somewhere like, let me mark 0. So let's say I mark 0 here, and then 5 will be like that. You can use a ruler. I'm going to move 0 a little bit over because 3 should be smaller. So the drawing for x greater than 5, I'm going to do 2 different drawings that way. That's the first one. I'm going to move this. So I'm really happy, you're trying it. So we're going to clear up any mistakes you might make in the future, or you'll feel rewarded for getting it right. So the first one is, oh no, that's not the right drawing. So the first one is x greater than 5. So I'm going to draw this like this. And this one I'm going to draw like this. So what I want is x greater than 5, and it only goes till 10. Now it's okay if you write it like this, but you could also write it like probability x between 5 and 10, but you don't have to, okay? Because this tells people, the reader, that it only goes till 10. And it doesn't add any information to you, particularly if you do that. So I'm just going to erase that to avoid confusion. And we need to find the area is equal to, there's no table. You don't have to put this in Excel, although it's probably in Excel. You can probably do this in Excel. I don't think I've done that, but what you're going to do is get the area of a box. So the area of the box is the height times the width. The width is how much here? It's just 5, right? The upper one minus the lower one in this area here. You just go. So because it's continuous, we can make that calculation. But what is the height? How do I figure out what the height is?
You need the total width.
Okay, good. So the total width.
The area is 1 for this distribution. So you need to solve for h using the h multiplied by width. So it's 10 minus 3.
Mm-hmm.
The total width, and then just divide 1 between the width, divide by 130.
Okay, so we need the total width and the height. And what will that give us? If I took the total width times the height of the whole box, what should I get?
That's equal the area, right?
Mm-hmm.
The area, which should be 1.
Why should it be 1?
Well, I'm assuming it's a normal
not normal, but a regular
Uh,
legitimate distribution, right?
Yeah,
So
and
for a legitimate distribution, it should be 1. We're going to put height times width. Usually alphabetical order, I do things so. Okay, height times width. So so that's 1. The width is, like he said, the upper minus the lower of the whole thing, right? The upper of the whole thing is 10 minus the lower, which is minus 3. Be careful with the sign that this is actually 13, right? So from here to here is 13. So even this drawing is not to scale. It's just to help us in making our calculations, understanding the concepts. I mean, it'd be better if I drew it to scale, but you're gonna see it would look weird. And I can't easily fit it on here. So that's 13. So what do I know? I know that 13. So height times 13 is equal to 1. So then that means that height, let me get rid of this x, because it's not an x, it's a multiplication, but let's just make it. It's okay, you got to know it's a times. I'll just make it smaller. Okay, so height is equal to 1 over 13. So what you got to do is you have to find out the parameter. Using the parameters, you find out the height. Looking in this local area, you find the width. And so, this is 1 over 13 times 5, or 5 over 13. So that is the probability in a uniform distribution from -3 to 10. The probability that x is greater than 5 is 5 over 13. Questions about that? So that thing that you needed to know was,
Sorry, Professor, can you repeat again the last explanation that you mentioned, the 1 over 13?
yeah. Yeah. So the thing that you need to realize is every distribution, all possible outcomes should be 1. We talked about that, right? So in a probability density, the area has to be 1. So the area of this one has to be 1. And knowing the width, we can find the height. Actually, the formula for the height is just this. Height is equal to 1 over L minus, upper minus lower.
Sorry, I got that part. The one that I didn't follow you was on the one where you are doing the probability, where you get the 5 over 13. That's the one.
So this is just in general, the height. In this problem, it's 13. Just be careful with the math there. And then you have to find the area here, it's going to be height times width. The width we knew was 5 because it was 10 minus 5 is 5. And the height is 1 over 13 in this case. And so we get 5 over 13.
Okay.
Now try for the other problem. Now that we did this one, what about the next one? It's a little bit easier. The height is the same. Right, Daniela, very good. Emmanuel, very good. Okay. So this is not so bad, right? So you need your parameters. Parameters are the minimum necessary information for you to solve for probabilities. In the exercises, in the review exercises, there's different shapes of densities, and I give you some instructions. And in a similar way, it's not uniform, but they have different kinds of distribution shapes. One's a triangle, one is a semicircle, and you can use them in a similar way to find the probability of outcomes. Okay, so for the second one, all you're going to do is the same thing. Oops. Height times width. The height is 113. The width is going to be between here and here. Again, upper minus lower, but it's going to be 0 minus 3, which is 3. So it's times 3. I'm doing this carefully because you can make stupid, dumb mistakes or little mistakes, errors, if you don't realize that this is continuous and I take the higher one minus the lower one, and there's that negative in there, but that's still a distance, a magnitude of 3, right? That's 3, even though we're in the negative. Okay, so that's it. Okay, so you can work with uniform, you can work with other shapes using the instructions, and you remember grade school because some of the stuff, the shapes you've learned before. You might not have memorized the rules, but you should feel comfortable once you know which rule to use. Okay. Okay, so that's it. Like basically that's an overview. You just have to learn how to work with each of these distributions properly, but it's a finite number of them. In the sense that once you learn the pattern, you can do this. The only distribution that remains for us to learn about together is the t distribution that comes in module 9. Okay, let me go back. Is that okay? So I'm going to go back to the notes. And I want to, before we go at 11:30, I'll go to 11:30. I want to talk about the other half of this course. So this stuff, this practice assignment, let me share this. This practice assignment that comes next, I cover this, and this is an excellent exercise for you to practice everything that you learned. The whole thing is good, but the first one is really great, I think. And here, see what I mean? You have some drawings here, and I tell you some rules, and you use it to find or to determine if it's a valid or legitimate density curve. The answers are all here. So try and do them yourself, and then use the answers to correct your work or correct yourself. There's a number of quizzes here. I didn't talk today about the general rules, but hopefully you've gotten that far and you've watched the videos about the probability rules. All right, so then I arrive here, Bayes. Did anybody get this far? The Bayes rule? Has anybody come this far? There's two remaining topics. One is Bayes rule and about conditional probabilities, and the other is, and it looks very intimidating, but it's not. I'm not going to put Bayes rule on the exam, but this is really important stuff. I think it's really important, and it's very, very interesting. So I do want you to spend some time on it. I had a lot of these problems in the quizzes, and I took them out because I didn't want to make students think it was more important than everything else. But I think if you the takeaway from here is if you understand this, you understand more than 90% of the population about testing and what probabilities mean in science, right? And in scientific diagnostic testing. And we went through the episode of the pandemic, and this played a really big role in our lives, understanding what is a positive test, what is a negative test, what's a false positive, what's a false. So take some time to review that. It's not too many pages. And I have the references here for the new bold text, but you can find the equivalent in the textbook online. Okay, so Bayes rule is not going to be on the exam, so don't freak out, but spend some time on it, learning it, appreciating it. Okay, Bayes rule. This is really important. Okay, the rules for means and variances. And I don't think my videos, the pre-recorded videos, they're very cursory. I just go through this and I repeat some of the stuff in here, and I don't think they're great. I have to think about the videos that I prepare for you in the live classroom setting. I go a little bit deeper with this, and I encourage you to watch it. I think what I want to do today, like when I do these overview meetings, I don't want to be repetitive. I just want to get to the point, right? And so what you have here, what we're getting at is, can we take information about one distribution and, like, because we spend time trying to follow a phenomenon, observe, collect data, and we determine a distribution of, like, for example, how many people hold an umbrella on a rainy day. You can have a distribution of rainfall that you derive, or you observe a manufacturing process and record when a robot arm in a manufacturing assembly line stops working. You can observe and collect data and then come up with a distribution to help guide your decision making, right? What if we make small tweaks to the distribution we already developed? Do we have to go through that whole process again and start observing? No, we don't. Okay, so these rules are a fast way to use a distribution that's already been established and make little changes and still know the parameters of that distribution, the mean and the standard deviation, for instance. So that's the idea here. Okay, so notice I introduced this, like, so this looks familiar, right? So this is the distribution I present you. These are the possible outcomes. These are the probabilities. What kind of distribution is this? Is it discrete or is it continuous? It looks a little bit different, but what is it? Discrete or continuous?
Continuous.
Well, look at how I actually wrote that there's 4 possible outcomes and their probability. So it is not continuous, because I usually cannot write that. I have to make a formula or something, right? Like in the normal distribution, I have a formula and I show it to you in the notes. But I give you a table and it's only a few values, because in fact, for a continuous distribution, there's infinite possibilities. How many possibilities are here? So here's an example. How many possibilities here? Just 4. Very good. So there's 4 possibilities. So there's just 4. So this is discrete. This is discrete. This is a discrete distribution. So having said that, this is the easiest way I can introduce this concept to you, is talk about a discrete distribution, but these rules apply to continuous distributions as well. Okay. Okay, so what we're going to do, so first of all, this is a distribution. These are all the possible outcomes. Being all the possible outcomes is as simple as I've made it. We can calculate the mean of this by the weighted mean, the weighted average. That's all this is. This is the weighted average. Do you guys see that? So looking here at this data here in this example, what's the expected value here? I have it there, but what's the expected value here? So what do you have to do? You have to multiply these across and add them together to get the mean. You can actually do that in the calculator. I can show you. And this can easily be done in Excel as well. But if we get the expected value here, I'll show you on the calculator. I'm going to write the numbers down first. I just have things going along and as opposed to down right now. Okay, so this is the data you're looking at here. But I could just as well write it like this, right? And then in my calculator, I can go to the stat mode. There's something there, so I need to clear it. And I can enter, I'm going to enter this as X and this as Y. And I can easily get the weighted mean by finding this statistic in the calculator. Did you see this before? So this is going to give me the weighted mean. So write that somewhere that you can find it so you remember. So 0.3 and 1 negative 0.4 and 0. And then the next pair is 0.2, enter down for X, and 3, enter down for Y, and 0.1 for X, and then 5 for Y. Then I ask for the statistics and I scroll up and that's the answer. So it does it for me in the calculator very easily. Otherwise, you have to multiply. You can do it in Excel. You can do it manually. And sum them to get the total. Which is not so hard with these small numbers. Okay, 0.8. All right, so what we found was the average for this distribution. Any questions about that? So that's what we found is the mean. And you can also find the standard deviation, but not in the calculator. You have to do it to go back and see how we did that. It was the weighted square deviations, the average of the weighted square deviations from the mean. It's a little bit longer process, but you can do that as well. So I don't stress that so much here because I usually give you the results. But so what's the deal? The deal is that if I know the mean of a distribution like 0.8 here, of this distribution, and I manipulate the distribution by either and or multiplying each value of the distribution by a certain number and or adding an amount to each of them. So if I perform a linear transformation that looks like this, multiply by something and add something, this is known as a linear transformation. And you can do that. You could say, okay, I'm going to increase the wins by 2. I'm going to double them. So doubling would be a 2 for a B. And then, but I'm going to add also $50 to all the winnings. So these are things that you can do to modify the distribution. How does that affect the parameters? That's the deal here. How does it affect the parameters? And the rule is, so here I go through and I prove it all. You don't have to prove anything, but you can read through that. You should feel okay to see it's just algebra. I just collect the terms. What is the rule though? The rule is whatever I do to the variable X, if I multiply by a number, if I add another number, I also do to the mean. So whatever I do to the variable, I do to the mean. It's the same treatment. If X gets multiplied by a number and something else added to it, I also have to do that to the mean, right? And this is like a proof here, and it's very important. So that's the rule there. So so any questions about that? Whatever I do to the mean, the values, I also do to the mean. And I present an example using the normal distribution. I make some drawings and things because you've seen this before. You've seen this where I take the normal distribution and I standardize it. What do? We subtract every value by the mean, and then we divide that by the standard deviation. That's similar. Okay, similar idea. What is the rule? What happens to the mean or the parameter of the mean if I take 2 different distributions and I add them together? That's the next rule. What if I take 2 distributions and I subtract them from each other? What happens to the mean? So this E, all the E means, all it's referring to is the expected value or the mean. What happens to the expected value? What happens to the expected value? So what does it say here? What do you read? What does this tell you? So let me tell you an example. So let's say I'm investing and I have invested in a certain company and I'm a shareholder in one company, but then I also am a shareholder in another company. The first company is called X and the next company is called Y. So I have shares in X and shares in Y. So I want to figure out, what do I expect in terms of what I'm going to get as a return? What are my returns from being an investor? How much am I going to make for every dollar I invest? What do I expect to get? Okay, so that would be the expected value of this. Could be I get 5% for X, and maybe I get 10% for every dollar invested for Y. So all this is saying that if I hold both of them, X and Y, the average is just going to be the sum of the averages. That makes sense, right? So yeah, I'm going to have 2 different stocks and one has an expected value of 5% and the other one has a expected value of 10%. So for every dollar I invest, I'm going to get a little bit from each. If I invest $1 in each of them. Okay, so I'm going to have 15% in that case. So I'm not putting numbers here. I'm just trying to get you to feel like, yeah, that makes sense, right? I'm going to get the average. So just be able to add them. So those are the 2 rules. And I just have these examples that I got from just to make it more tangible. And I just have these examples. And then I talk about the variance. So what's the rule for the variance? So I'm just going to skip over all of this, but I do talk about this in the videos and I spend some time here. I'm just going to go here to the examples because we have a half an hour. Now, this is very important for the exam, okay? Even though I throw out Bayes' rule for the exam, I am going to put on the final exam 1 question that looks like one of these. So you need to spend some time understanding these. And there's 5 exercises. I think there's 5 here. There's 1. There's 6 exercises, okay? So there's rules for means and rules for variance. So here's an example. Each year, so did anybody get this far? I just want to show you the end point. So you're going to spend hopefully this weekend wrapping this up and understanding this so you can continue and go on to the binomial for next week, or the module 8 for next week. So anybody get this far? Let me see. No one. All right, so let's see if I can make it. Okay, make it easy for you. All right, so read this problem. Read it to yourself, and then I'll. So I don't know the distribution. I don't know the shape of the distribution, but I know the parameters. Okay. I'm told that the average duration of employment for employees of this company is 6.7 years with a standard deviation of 2.4. The mean and standard deviation. And I'm going to use the duration of the employment to determine the Christmas bonus that the employees should get. And what I'm going to do is take the take how long they've worked, multiply it by 100, and add 500. Okay, so this is a linear transformation based on the number of years of employment. So what happens to the mean and standard deviation of the years of employment? What happens in terms of what's the average Christmas bonus and what's the standard deviation for the Christmas bonus? That's what we want to find out. You guys want to guess? So whatever you do to the variable, you do to the mean. And then I'm going to talk about the standard deviation, which is a little bit different. Okay, let me show you. what it is that I do. Okay, so this is the important information I've written up. So they tell you that we're going to get a new variable from X. This is number of years of employment. And you're told that the average years of employment are 6.7 and the standard deviation is 2.4 years. From there, we want to find the mean of this, of the bonus. But what is that? That's just based on the original. Now, rather than having to, because we observe data on employment over the years, right? And we came up with this, the mean, and that's the standard deviation. We made these calculations with all the data. Do we have to give out the Christmas bonuses and then observe again, or is there a pattern? There is a pattern. Because all we have to do is keep in mind that whatever we do to the mean, whatever we do to the variable, we also do to the mean. So all I do with this E, this is like, it's like they refer to it like an operator, right? The expected value. The shift of the $500, the extra $500 is there, and the multiple of 100 is right on, gets multiplied to the mean. So if I multiply by 100 and add 500 to the years of employment, I'm also doing it to the mean. So then that's pretty easy. I just plug that in. I don't have to observe. After doing that, I don't have to observe for a long time the pattern of the pattern that I've observed for employment, years of employment, gets transformed into the bonuses. So this is the transformation here. This X becomes a mean, same equation, everything the same, and then I find it out. So what is it? It's all in dollars. Good. Does everybody get 1170? Let's take a moment before we get to the variance, unless you have questions. Let's see if you have questions. Everybody okay with that calculation? So what we did was we took a distribution. Imagine there's a distribution. I'll just make it even like this. I have to put my glasses. This is X. Let's say the middle is, they told us 6.7. And what I'm going to do is multiply every value of X by 100. What happens to the distribution when I do that? What happens to the mean? Does it look the same? What happens to the mean? Let's start there. 6.7 times 100 becomes what? $670, okay. So I'm going to replace that with 670. And then what happens to the rest of it? If that's 670 and one standard deviation over is going to be 6.7 plus 2.4 equals 11, 9.1. Okay, so 9.1 is one standard deviation here. What does 9.1 become? If 6.7 becomes 670, 9.1 becomes what? $910, right? So is that going to be here? So this whole thing, I mean, I could change the scale of the whole thing, but it's better to show you to illustrate this. This is going to be much more spread out. So one standard deviation is here, 9, 10, right? And it goes flatter because it all has to be 100% underneath. Everybody okay with what I'm doing so far? 100 times. So it makes it flatter. Everything spreads out. Is that okay? This new distribution. So if I change every value by adding 100, what happens to the standard deviation? Does it get multiplied by 100? Oh, this is a problem here. The V operator is not exactly what I want to use. So this is much, so, they're greater by a multiple of 100. What about the 500? If I add 500 to every value, do I affect the spread of the distribution? I'm going to just say the standard deviation because it's not the variance. The variance is a different thing, but the same result. But anyway. So if I add 500 to every single value here, what do I get? $670 plus 500 makes 1170, right? So I have this, so this is my final distribution. Oh, I can't, I gotta play, let me make this look more like that one. The mean is 1170. But did the shape of did the pattern change? Did the standard deviation change by adding 500? Even if I add 500 to the 910, one standard deviation away, this becomes 1410. Did the standard deviation change when I added 500 to every value? Does it change it? So we went from X, multiplied by X made it more spread out. So the standard deviation is greater by 100. But did the shift affect the standard deviation? The flatness? The spread outness? Okay, so that doesn't change. So what the result is, when you're talking about the standard deviation, this shift factor has no effect. All right. The standard deviation of 500 plus 100x is just 100 times the standard deviation of x. That's it. And it's just because of this principle. So in the case of the mean, whatever you do to every value, you do to the mean. In the case of the standard deviation, whatever you multiply to every value, you also multiply the standard deviation. And shifting doesn't affect the spread. All right, so with that, finish this problem. The standard deviation was 2.4, so it's 100 times 2.4. And I apologize if my drawings look a little funky, but I hope they make the point, the main point that I'm trying to make. 240, is that right? 2. So we don't have to observe bonuses for a period of time to know the mean and standard deviation of bonuses. We just have to know these rules. So this is a rule of mean and variances for a linear transformation. Linear transformation involves multiplying a scalar and adding or shifting the distribution. Linear transformation is because it looks like a line, right? A plus bx looks like a line. So that's the first set of rules you got to work with. The second set of rules you have to learn are when you add and subtract variables to create a new variable. Add, subtract variables, and then also, yeah, and then combining that with linear transformations. I put everything together. So let's look at one more example before you go. Okay, let's look at this one. Okay, what is this all about now? Okay, so there's some rules that you have to learn, and you can put them on a sheet, you know, put all your rules together, make for yourself an outline of what you learned in this class. And from here, you're going to take the rules of means and variances and the sum of variables and the subtraction of variables and the linear combination of sums of variables. All right, so let's first, so that's where we're headed. I'm going to take you to my iPad for a moment. Okay, so let's do this from some sort of intuition that what we learned about the rules of linear transformations. So if I create a new variable, so I'm going to create a variable, oh no, I'll call it Z. And I'm going to create it from taking a multiple of a variable X and adding it to a multiple of a variable Y. What do I know about, okay, and I know the mean of X and I know the mean of Y, and I know the standard deviation of X and I know the standard deviation of Y. So these are all available to me. So what will be the mean of the new variable Z? What do you think? Let's just try and see. Just take a moment. And what do you think that's going to look like? So carrying with the rule that I gave you, whatever you do to the variable, you also do to the mean. What do you think it's going to be here? So I'm going to take A and I'm going to multiply. Well, actually, I'll use the E's and then I'll fix it. So I'm going to multiply A to every value of X. So then I also do it to the mean, right? And I'm going to take every value of Y and multiply B. So I'm also going to do that to the mean. So that I write as E mu X plus B mu Y. So think about that. Copy that out. Whatever I do to every value, I do to the mean. I'm going to say however I transform So is everybody okay with that so far? So for instance, for example, I'm going to keep you guys a little over to finish. If you have to go, just go ahead. And just watch the tail end later. If you can stay like 10 minutes, I can finish this properly. Okay, so let's say, for example, I'm going to create z equals to 3x minus y. And what is the mean of z then? It'll be 3 mu x minus mu y. Like the minus 1 is just, so in here, a was 3 and b was minus 1. That's the idea. Just to give you an example without complicating it with the means. So I'm going to just write out the rule for mu ax plus by. I just, whatever I did to the x and y, I do to the means. And now let's talk about the variance. What about the variance of z? So I'm going to talk about the variance because I have to make a particular point, not the standard deviation. Although it falls out of this, but okay, the variance. This is a z. The variance of z, the variance of ax plus by. Now, is it the same thing? Is it going to be is it just going to be can it just be like that, do you think? It's my question for you. Do you think it's just like that? That's simple? So usually you're learning in statistics that most of it is pretty intuitive, but there's some things I have to clarify. That's why there's academia or there's it's what we explore, right? Little variations from what seems to be right. We need to clarify for in cases that it's not exactly going to follow from this rule, what happens here. So it's not exactly that, okay? It's not just going to be like whatever I do to X and Y, I do to the variance, because we already learned that variance is a specific thing where I'm looking at the spread. I don't really care about if I shift the distribution, that doesn't affect the spread of the distribution. So let's take a moment and remember what the variance is. So I'm going to do that using the formula for the variance that we learned for the sample, just because, I don't know, just easier to write up. So if I have this, that's the variance of X. Everybody agree? Let's try and remember. That's the variance, right? The standard deviation where I take the square root, but I'm just going to look at the variance. Everybody okay with that? Yeah? Remember? Now let's take let's multiply A to every single value. So how will I do that? Let's make a new variable where I multiply A to X. So I'm going to take every single value and multiply A to it. And what did I say before? Whatever I do to every value, I always also do to the mean. So that would be like that, correct? Are you guys buying it so far? Well, whatever I do to every value, I also do to the mean. So that mean here, the sample mean. So now I want to write this expression in terms of, I want to write this one in terms of this one. So I'm going to do that by removing the A. How do I remove the A? I'm going to factor out the A. So what I'm going to do is rewrite this. I'm going to factor out the A out of this. But I still have that square over there. Remember the rationale for the squaring, right? That was to do the square deviations from the mean because of the nature of the mean. That it was if we didn't square it, the average of the deviations would be 0 every time, because just of the whole idea of what the mean as a center of gravity is. So finally, the A can come out, but what do I have to do to it to take it away from here and bring it in front? What happens to get the A out? What do I have to do? Anybody? Just like I had to square the deviations from the mean, I have to square the scalar in front. Okay, it also gets squared. So it's going to be here by itself, away from everything else, but it had to be square. So VAX is equal to A squared VX. Now, we didn't see that when we were dealing with the standard deviation that we just discussed. When I discussed the standard deviation of AX, I just did this. It's just A times standard deviation of X. I just wrote it like that, right? So let me write it. Let me do it with the symbols. So it was like this, and then it's like that. But when I do it with the variance, I have to have this squared here. Why? Because if I take the square root, that will give me A, and the square root of variance of X will give me the standard deviation. So it's like two things that you need to remember, or you need to remember with the variance, this gets squared. Okay, so that's really important. And how does that affect my result over here? So the question was, is whatever I do to the variance, whatever I do, to the variable, I also do to the variance? Well, no. What do I have to do? How do I fix this? What should I do? What's wrong with this? What's missing?
The square.
The square. So the square is missing for starters. That square is missing. And the other point to make is when you're figuring out the variance between two variables. So if I have if I'm an investor and I have one type of investment, asset X or the stock and company X, and I have stock and company Y, I care and I hold them both. I'm going to be exposed to the variance or the volatility of the returns from X and the volatility from the returns of Y, but also those two assets have a covariance, so that they're not exactly separate. They might be related. All right, so this formula here that I wrote only applies if X and Y are independent or not correlated in any way. If they are dependent or they are correlated, there's a different formula. All right, so what's the different formula? In general, I'm going to move all this away from here. This is just the background, why there's a square there, and it's back to why we square. Why we square the deviations from the mean. So this is true if X and Y are independent, but the variance of AX plus BY in general is equal to A squared VX plus B squared VY plus 2 AB covariance X, Y. And I guess I'll stop there, but once you get that, so the main things that you've learned are whatever you do to the values, you also do to the mean. The standard deviation is only affected by the multiples, not by any shift factors or adding or subtracting. So then the third thing is combining variables, looking at the variance as opposed to the standard deviation, okay? This is only true with the square values, just similar to whatever I did to the values, I also do to the mean. Similar with the variance, except that I have to remember about the square deviations from the mean. This only works if they are uncorrelated. Otherwise, we have this extra term in there. So I will stop there, but hopefully that's the most simple we can get. And then all I do is I elaborate a little bit more of how to work with this. So for this weekend, spend some time with this, doing those 5 or 6 exercises at the end and understanding them. They're technical, but that's the epitome. Like, and I will put one of those on the final exam. You can spend a little bit of time now, but always go back there because you need to be good with these rules of means and variances. Can't walk out of a statistics class at this level without understanding how to combine variables and what happens to their parameters when you do so. Okay, hopefully this was helpful in an overview because it becomes overwhelming. There's lots of material there, but you should be able to answer questions, and that's the most important thing, that you can apply it. You don't have to be an expert. All right. Okay. So keep in touch. I told you I would write you if I would let you know if students had questions. I only got one question from a student. I didn't share it with you, but I guess I could share that in an email. But otherwise I didn't get any questions. I have to check if anybody's writing in the forum, but the tendency is students don't use the forums unless I force you. So just write me an email if you have any questions. If you want to meet this week, If you want to go over any parts that are really not, that you're having trouble with, or you're just not picking up, we can get you over that hurdle that way on an individual basis. Okay. Otherwise, I'm going to put this video onto YouTube. And as I mentioned before, if you guys don't want to appear on YouTube, I can make these private. It's just easier to find them if they're public. And I don't think anyone's really looking for you. But if you don't want to be on video, just let me know and I can make these private. The links are all in the Moodle and only going to be visible to you. Okay. Have a good week. Have a nice weekend. Keep studying. Keep me informed.
Professor, I have a question before we
Sure.
go.
Yes.
Do we get, like, partial points for the exercises that we did wrong in the written submissions of
If
the
you want points, contact me, write me, and we can look at it. Okay.
just
If you
wanna-
think that you deserve some points, that's what those evidence are for, so you can make your case. Okay.
Okay.
And then other people, the other people will benefit because I'll change the scoring like I just did. And you saw me scoring, right? I changed the score first. So if I think that you deserve some points, yeah, like everybody benefits. So have a look at your exams. Okay. Okay.
Professor, you have a
Bye. Good. Bye.
Professor, when are we going to see like the points for the attendance?
I did put them. You didn't see it? Is
No,
it
I
not
don't
visible?
know.
I put them in Moodle.
Let me check again. Maybe I just didn't see it, but I
Yeah, I
thought
put it last week because I was way overdue.
let me
let-
check again. Just
Yeah.
a second.
I can see it, but maybe it's not visible to you. I'm going to project it because sometimes I do that and it looks like you can see it and you can't. It's right there at the top. I have the totals.
Well, I can see it either, just,
Really?
yeah,
You like look. It's right here. No?
in anuncios, no,
It's blank?
yeah, it says
Oh, wow.
anuncios right afterwards, syllable.
Okay, so let me check the programming here, what I did
But I
here.
need to send you like a screenshot or,
Okay, I'm gonna see. It's weird. Let me edit. No, I believe you. You can see it, but I don't know why. It's weird. Let me change this. Restrict access. No. No, it's not restricted.
Availability is high from students.
Oh, thank you. I never said that. That does some default. That's weird. So I got to go through everything. Well, what I can do is I usually can change the mode to see student mode and I can see, but
Yeah, I can see it now. Thank
all
you.
right. Okay. I
maybe
posted them on the 4th last week. Okay. So have a good week. Thanks for letting me know.
thank you, bye.
Bye.
Have a nice day. Goodbye.
Have a good weekend.